Hello everyone! Did you know, with just 4 numbers and a grid of cells, you can create an infinite amount of complex behavioral patterns never before seen by human eyes? Add a couple more numbers and grids, and suddenly, you have life itself. Thanks to GameMaker for sponsoring this video. GameMaker is the all-in-one solution to your game development needs, popular with both industry professionals and first-time game developers alike. My videos are often about complex shader programming techniques, with most viewers assuming that a heavy-duty engine is a requirement, but GameMaker is actually more than capable of advanced custom shader effects. Aside from shaders, many industry-defining games were made with GameMaker, such as Undertale, Hotline Miami, Spelunky, Risk of Rain, Valhalla, and my personal favorite, World of Horror. Learning and experimenting with GameMaker is totally free. You can export any project to all non-console platforms for non-commercial use as much as you want, and if you decide you want to make your dream game in the engine, GameMaker has a one-time perpetual license, no cringe subscription or runtime fees involved. Be sure to try out GameMaker totally for free using the link in the description and start building games today. Now, back to the video. On August 2nd, popular VTuber Dokibird announced the start of her community game jam, an event where you try to create a game according to a theme within a given time limit, in this case, 2 weeks. The theme was chain reaction. The examples provided were more narratively focused, given that the jam was clearly meant to produce funny moments for Dokibird to react to on stream. I'm an INTJ though, so when I think chain reaction, I think of chemistry, and when I thought of chemistry, I remembered my old project implementing a model of the Belousov-Zhabotinsky reaction, a very cool, recently discovered chemical oscillator. The simulation of this reaction is what's known as a cellular automaton, a model of computation that divides up the universe into a grid of cells, with each cell deciding its next output based on the previous output of its surrounding neighbors. Cellular automata often makes use of very simple rules, but despite the simplicity, the resulting behavior of an automaton is wildly unpredictable and chaotic, ranging from seizure-inducing flashes to seemingly realistic organic structures that look like bacteria. And since automatons function based off of a reaction to their neighbors, I thought a game centered around this topic fit the chain reaction theme pretty well. 2 weeks later, I have learned that you probably shouldn't try to make a game centered around cellular automata. This topic could only be described as a cognitohazard and a total tooling nightmare. Despite the hardship, I persevered, and I'm proud to show off my new game, a fully customizable, real-time, 2-state, multi-neighborhood cellular automaton where you create your own cell organelles to see what happens. As usual, I did everything for the game, from the software design to the programming to the UI to the music and sound effects. I'm sure one of these things will be exciting to you. So how do these automatons actually function? Why are they so hard to work with? And how did I try to solve these problems? In the 1940s, at Los Alamos National Laboratory, something very important was under research and development. Stanislaw Ulam was studying the growth of crystals, utilizing a lattice network as a model. At the same time, another very important project was underway. John von Neumann was sitting and thinking really hard about self-replicating machines. Von Neumann eventually realized that designing a robot that could build a copy of itself was a pretty difficult problem. Mechanisms aside, just providing the materials to the robot to replicate itself with seemed to be an impossible task. Ulam made the suggestion to von Neumann that he should try utilizing the lattice grid technique to create a simple model of self-replication, but nothing would really come of it for a while, and instead, Ulam and von Neumann finished up their side work at Los Alamos. Nearly 20 years later, Ulam and von Neumann would be back at it again, but this time trying to create a model for fluid simulation. This model worked by dividing up the fluid into a number of discrete units, like some sort of lattice grid of cells. The motion of the liquid was modeled by each cell checking the behavior of its neighbors to determine what it should be doing itself. This method of fluid simulation would become known as the first cellular automaton system, and it's actually a technique still utilized today for simpler 2D fluid simulations. This makes sense because if you think about it, the cells are essentially just the dx in an integral, which should make you wonder, if this automaton was an accurate model of reality, what would happen if we reduced each cell to some infinitely small size? It would no longer look like a cellular automaton, it would just look like real life. The logical extension to this thought is that reality itself and the entire universe could be the deterministic output of a single cellular automaton, an idea proposed by German computer scientist Konrad Zuse. Don't ask what he was up to during the 40s. Von Neumann would take the system devised for the fluid simulation and expand it to finally realize his dream of a self-replicating machine. The von Neumann universal constructor was a 200,000 cell configuration, with each cell having 29 different possible states. The automaton could reproduce its own configuration forever. This innovative model developed by Ulam and von Neumann would stay confined to academia for another decade, with the greater public not really knowing or caring about cellular automata until the 1970s, when mathematician John Conway's life was ruined with the publication of his invention, The Game of Life, in a Scientific American article. Conway's Game of Life is debatably the most famous cellular automaton and is much simpler than von Neumann's absurdly complex universal constructor, with only 2 states per cell compared to von Neumann's 29 possible states. The simple nature of the Game of Life and the seemingly infinite possible ways it could evolve caused the game to become massively popular, with tons of people trying to come up with interesting new patterns. Conway himself didn't even know the full potential of his own creation, believing it impossible for the game to be able to model self-replication until he was later proven wrong. Not only can it accomplish von Neumann's life's work in a much simpler fashion, the Game of Life can model entire computers, meaning the Game of Life can simulate itself within itself. How thought-provoking. I'm sure we all know the rules to the Game of Life, but it happens to be the entry point for all of the tech I made for my game, so let's do a quick review. We will now create the universe. Unfortunately, it's empty. Before there can be anything, we must first define what it means to be. Our universe will be two-dimensional, and at the very tiniest, most minuscule level, everything aligns to a lattice grid of square cells. The cells can exist in one of 2 possible states, 1 or 0, on or off, alive or dead. It depends on how emotional you want our experiments to feel. It turns out that our universe was never empty at all. Everything is just dead. The initial state of the universe is traditionally the only thing we have direct control over, which in our case is just going to be some random noise. Unfortunately, nothing can happen if we can't do anything, so here comes John Conway to tell the universe how to live. To progress the world, we take the previous state of the universe, in this case the initial noise, and pass it through a function of our design. Every single cell of the universe is going to check each of its direct neighbors, including diagonals, and count how many are alive. If there's 2 or less, the cell dies by underpopulation. If there's 2 or 3, the cell stays alive if it isn't dead. If there's exactly 3, the cell is born. If there's 4 or more, the cell dies by overpopulation. Now that the cells know what to do, we can see the Game of Life in action. Fascinatingly, even our random initial states transform into interesting structures with unique behaviors. It's up to you whether you consider these cells to be part of one big evolving body, or a bunch of tiny individually formed bodies of the same species cannibalizing each other. These little guys are called gliders, and through their valiant eternal sacrifice, the world can grow sophisticated enough to become functional computers and eventually simulate itself entirely. The initial state of the universe is probably responsible for whether this can happen. I say probably because there is no definitive method of determining if a given initial state will eventually result in such a complex outcome given enough time, but I think it's safe to say our noise probably isn't going to give us that result within the span of our lives. If we wanted to further study the Game of Life, we would start improving our control over the initial state to more reliably create stable structures and observe how they evolve. But I'm more interested in improving our control over the rules of the universe. The rules of the Game of Life are a little verbose, so let's rewrite them in a simpler form. If a cell has 2 to 3 active neighbors, the cell will keep its previous state, which I will refer to as stable. If a cell has 3 active neighbors, the cell is born. To make our conditionals more aesthetically pleasing, we can write the 3 as 3 to 3. Otherwise, the cell dies, or in more specific terms, any amount of active neighbors outside of these 2 ranges will kill the cell. But if our default cell value is 0, then this is implicit. Our 4 rules have now become 2, and if we replace our ranges with 4 variables, then we get a handy-dandy function describing all possible variations of the Game of Life, which makes it easy to see how things might change if a cell were to stay stable with something like 2 to 4 interactive neighbors instead. Already you can see that slight changes to the rules have massively different outputs, but most of them aren't that exciting. In the 1980s, Stephen Wolfram attempted to classify these automaton rule sets based on their vibes. Class 1 automatons are those that evolve into a stable, homogeneous state. Class 2 automatons evolve into stable or oscillating structures. Class 3 automatons evolve into total chaos. And lastly, Class 4 automatons are the ones we're looking for. Rules that evolve into structures that interact and behave in interesting ways. The game of life is a Class 4 automaton. Wolfram thinks that any Class 4 rule set should be capable of universal computation, but good luck proving that. Unfortunately for us, almost all rule sets within this domain are very boring. I checked nearly every single one by hand, and I didn't find any as interesting as the game of life. It seems there's no other Class 4 behavior to be found here. People figured this out pretty quickly and sought out other ways to modify the rules. Canadian computer scientist Brian Silverman decided to add a third state for the cells to exist in, resulting in the automaton Brian's brain. Others turned their eyes to the neighbors that our automaton looks at, which I was more interested in. The problem with our automaton is that there isn't much data to work with. Any cell can have up to 8 active neighbors, which isn't a lot, so our rules are very sensitive to even mild changes, causing massive overgrowth, seizure-inducing oscillations, or instant death. If we checked a greater range of neighbors, then hopefully we can find cooler rule sets. The set of neighbors that our automaton checks is called the neighborhood. Our current setup is a Moore neighborhood, where each cell has 8 neighbors, but there's lots of others, such as the von Neumann neighborhood, which doesn't include diagonals. Anything can be a neighborhood though. We don't have to confine ourselves to this 3x3 grid centered around the cell. We can go as big as we want, checking any cells within the bounds. This circle could be a neighborhood. This random noise could be a neighborhood. This bird could be a neighborhood. A collection of automatons called Larger Than Life explored the idea of a kernel size beyond 3x3. The most popular is called Bugs, with a whopping 11x11 kernel and the following rule ranges. Bugs definitely has the vibe of a Class 4 automaton, with these little inchworm guys that travel in a single direction forever. There's lots of stable structures as well, and these interesting inchworm variations that will appear to explode, but instead transform into an inchworm going the opposite direction until it does it again in reverse. Unlike the game of life, there are interesting adjustments to the ranges that can be found. While it might not be Class 4 level, the patterns are much more interesting to look at, but most movement always ends up looking kind of the same as Bugs without the stability. As cool as this looks, I'm more interested in how the shape of the kernel impacts the result. Bugs is a square kernel, but what about a circle or some other shape? Unfortunately, this is where things get complicated. While we could hardcode complex kernel shapes, that isn't very easy to work with or customize. I'd rather have some sort of user interface to easily paint kernel shapes with. Because the automaton simulation is on the GPU, we'll have to create quite the pipeline for getting our user-drawn neighborhood from the UI to the shader. I decided to start on the UI side of things and figure out how to get it over to the GPU later. The first roadblock is choosing how large our customizable neighborhood space will be. Hard-coded kernels are actually easier to work with in some ways, as the large 11x11 kernel size of something like Bugs is trivial to implement, but as an interactable grid of 121 buttons, it'd be tiresome to have to click every single one. Clearly, a space large enough to support the Bugs kernel is a requirement to continue our experiments though, so I decided on a 15x15 customizable space for reasons that will make sense later. Applying my graphics design skills from college, I opened up Photoshop and made a 15x15 grid. The next roadblock is deciding how we want to implement the ability to enable and disable individual neighborhood cells. There's very few good ways to accomplish this, and lots of bad ways. A 15x15 grid means 225 individual interactive zones. The engine I'm using, Godot, offers some built-in UI tools, so while I could copy and paste 225 unique buttons into the scene, that doesn't really seem like the best choice. Instead, I decided to make use of a popular structure in 2D games called tile maps, which every engine should hopefully have its own version of, so I don't have to make my own. A tile map is essentially the same thing as our 2D lattice grid universe. Each tile indexes into a texture atlas to get its texture, making it easy to paint 2D worlds. In our case, we'll be using it to paint our neighborhood. This means we need a texture atlas, so once again, I made use of my graphic design skills and created a 2x1 texture. The first pixel is black, the second pixel is white. With the texture imported, the tilemap editor already demonstrates the functionality we're looking for, but we needed to do this while the game is running. At runtime, when we are hovering over the tilemap, map and click on a tile, we convert the mouse position on screen to the coordinates of the tile within the map and swap its current value. A 0 index is black, a 1 index is white. With this method, we now have just one big button acting as 225 individual buttons, which feels a bit better. To make it easier to use, we can layer our grid texture on top and create a second tile map with reduced opacity that highlights the center of the neighborhood as well as the tile the mouse is currently hovering over. Now that we can draw our own kernels, we have to figure out how to get the tile map data over to the GPU. Just like the button dilemma, there are many ways we can prepare the neighborhood data for the GPU, the most obvious of which is with a texture. A texture is a grid of pixels, essentially no different from our tile map or automaton universe. We could easily put the neighborhood into a small 15 by 15 texture. If you remember from my Kuwahara filter video, using such a small texture can be a disaster for performance when we will be sampling it many times. This is because sampling textures is relatively slow. It takes time to retrieve the memory, time we'd rather not spend if we can help it. Instead, we'll be doing something a bit more clever, but first we need to learn how computers actually store information. At the very lowest level, everything on your computer is represented as a sequence of ones and zeros, also known as binary. Each individual 1 or 0 is referred to as a bit, and a collection of 8 bits is a byte. Generally, you have control over this when you're programming. I can define an 8-bit, 16-bit, 32-bit, or 64-bit integer depending on the amount of data I need, but the default for everything is usually 32-bit. If you recall from earlier, the cells in our neighborhood can be one of two possible states, 0 or 1, no different than a bit. So could we cleverly pack our neighborhood into one of these bit strings? Our grid is 15 by 15 or 225 cells, unfortunately much greater than our limit of 64 bits. But if we isolate a quadrant of the neighborhood, then coincidentally we now have an 8 by 8 grid of 64 cells, which fits perfectly into a 64-bit integer. If we overlay our 64-bit string onto our quadrant, it should become pretty obvious how this mapping will work. Any active cell of our neighborhood will become a 1 in the bit string. To activate specific bits of a string, we need to make use of some bitwise operations. First, we calculate the bit index of the cell. Then we take the number 1, which looks like this in binary, and use a bit shift operator to move that first active bit over to the corresponding index. We can't repeat this process for adding the next active cell, because if we did another bit shift operation, then the cell we previously activated will also be shifted. To add more activated bits to our string, we need to use a bitwise OR, a logical operation that compares each bit of two strings and outputs a new string with whichever bits were active in either string. This will activate new bits without affecting the others. We then repeat this process for the 3 other quadrants, and we have 4 64-bit strings representing our neighborhood, a whopping 32 bytes of data. Here's what the game of life looks like as 64-bit strings, and here's bugs. Not very exciting, sorry. Next, we can send this over to the GPU very easily with a Vulkan feature called push constants, a very small amount of data that travels to the GPU from the CPU along with the command. It's basically free. Now that our GPU has the neighborhood, we've got to do a bit of work to actually use it. We're essentially going to repeat the process we did to encode the neighborhood bits, but now for the actual active cells within the 15 by 15 grid surrounding a cell. With a bit string representing the current active neighbors and the bit string representing the neighbors we care about checking, we use a bitwise AND logical operation to produce a new string containing only the active cells within the neighborhood. Then, to get the total number of active cells, we sum the bits by ANDing our string with 1 to cut off every bit other than the first index. If that bit is active, we get 1 as a result, otherwise 0. Then we add it to our total sum, then shift over by 1 bit to check the next cell, repeating 64 times. Once we do this for all 4 quadrants, we will have the sum of active cells within our custom neighborhood. Then we compare with our custom rule ranges, and we have the same thing we had before, but now entirely controlled by the user interface. Unfortunately, my implementation has a big flaw. Because our quadrants have overlapping boundaries, we waste a lot of space masking off the edges of the other quadrants, so we don't count boundary cells twice. It would have been better to think of everything as a 16 by 16 grid with a 1 cell offset to center it. Should be easy enough to change though. Now that we can customize the neighborhood, finding cool looking automatons is much easier, but it's still annoying to have to work with all of these cells individually, so let's try making it a bit more usable. First, let's add the rule ranges to our grid. The left range will control when cells are born, and the right range will control when cells are stable. Left clicking a number will increment it, right clicking will decrement it, and since our ranges can technically go from 0 to 225, clicking enough to get up there is tiresome, so I added the ability to click and drag to make fast faster adjustments. The space to the left of our rule ranges gives us some room for a toolbar, so I made a couple little button icons. The first button will enable and disable the neighborhood, visually communicated by reducing the opacity of the grid. The second button will clear the neighborhood, so you don't have to individually click everything off. How convenient. The third button will draw a square of increasing size with each repeated left click, while right-clicking will erase a square of increasing size, making it much easier to create larger patterns. The fourth button does the same thing, but a circle instead. The fifth and last button is for my gamblers. It will randomly enable and disable cells. How exciting. For the simulation itself, I added a little sidebar with a button to play and pause, a zoom button, and directional keys to move around the world. Now our UI is looking quite a lot more functional, and it's much easier to use, but things are getting pretty boring already with just this one neighborhood to customize. I think it's time we add even more complexity. So far, every automaton we've seen has been a single neighborhood system, but it doesn't have to be that way. What would it look like if we combined the game of life with another automaton like bugs? First documented in 2014 by developer Slackermans, multiple neighborhood cellular automata is just that, a system of multiple neighborhoods with their own rules applied at the same time each generation. Because of our genius software design, adding more neighborhoods is trivially easy. We've got enough space on screen for 4 neighborhoods. Since we're using push constants to send the neighborhoods to the GPU, we have to be mindful of the memory limitations of the feature. Vulkan guarantees at least 128 bytes of data. Conveniently, our 4 neighborhoods of 32 bytes each equates to 128 bytes in total, a perfect fit. On the GPU side of things, we only need to scan for active neighbors once. From that bit string, we can apply as many neighborhood masks as we want, summing each one individually and applying the corresponding rules. Unfortunately, one downside of this implementation is that the last neighborhood sort of has the final say in things. If its rules were to kill the cell while a previous neighborhood would create one, the death would take precedent as it is applied last. Regardless, now we can see what it would look like if we combined the game of life with bugs, and the result is not that exciting. Don't let this disappointment get you down though, as multi-neighborhood automata feels like the first big step towards a generalized simulation of organic life. All the other automatons so far have modeled birth, death, and movement all in one single neighborhood and rule set, but now we can separate these functions into multiple neighborhoods to get more complex and interesting results. A basic multi-neighborhood automaton looks like this, where one neighborhood births new cells at a very wide range and the other kills off the excess growth. Already we see what looks like class 4 behavior, with these little guys appearing to move in one direction forever. As far as I'm aware, I'm the first person to discover this rule set, and you are the first people to see it. These creatures are sort of like my children in a way. I have named them wisps. Unfortunately, we have to kill them all to continue our development, so let's move on to making this game feel like more of a game. My final addition to the UI was a saving and loading system for the neighborhoods. Since we're generating it CPU side, it's trivially easy to save it to disk and load it at runtime too. I also put in a little bar showing the current seed for the RNG, which you can re-roll for endless entertainment. To complete the visuals of the game, we need to do something about the harsh black and white contrast. While it looks cool for a little bit, your eyes will quickly get strained from staring at this. If you remember from all the way back in my Ludwig Jam video where I made the dating game, I created a whole bunch of 1-bit color palettes to randomly select from each time you started a run to add visual variety and reduce eye strain. I wanted to reuse that idea here as well, but apply what I learned from my video on randomly generating color palettes so that I don't have to go through the trouble of making my own. In that video, we learned that the OKLab color space is generally ideal for randomly generated palettes because the perceptual brightness of a color stays consistent across the hues, unlike other color spaces where some colors might appear brighter or darker than others despite having numerically similar brightness values. Godot has the OKLab color space built into their color library, so we can easily generate OKLab colors from a hue, saturation, and lightness value. Using our seed from the UI, we randomly generate a number between 1 and 3 to decide if our color palette is monochromatic, complementary, or tertiary. Then we randomly generate a starting point for the hue, 2 saturation values for both colors, a random lightness value on the darker end for the first color, and a random lightness value on the brighter end for the second color. If we're generating a monochromatic palette, then the hue stays the same for both colors, and the only difference will be saturation and lightness. If we're generating a complementary palette, then we randomly decide which color will be the complement and set its hue to the other side of the color wheel. If we're generating a tertiary palette, then we randomly decide which color will be tertiary and set its hue to a small distance away, randomly left or right. Now, every time we generate a new seed, we also get a new color palette associated with it. Don't like the color palette? No need to fear. You can roll for more color palettes for just $4 per spin. Roll 10 times, and you'll get a guaranteed complementary palette. This finishes up the visuals of our game, but we're still missing arguably the most important part: sound effects. I've been playing piano for almost 2 years now, so this time I really wanted to challenge myself and actually make a real song for the game instead of just using noise. The problem was that I had no idea what kind of song to make. I wasn't really getting any specific vibes from my game. If anything, the absence of music would probably make the most sense. While the game is about designing life, the vibes are ultimately lifeless, but not in a particularly sad way. It just is what it is. So I asked my music teacher for some advice, and he said when there isn't any specific emotion to go off of, we should try to make use of suspended chords. A chord is a collection of notes. For instance, C major is these 3 notes. If we moved the middle note a half step down, we would get C minor. Major chords often invoke happy feelings, while minor chords often invoke sad feelings. But if we simply don't use those 2 specific middle notes and move a half step down or up, we get a suspended C chord. Not quite happy, not quite sad. It's kind of just there. Next, we need to decide on a scale to base our song in. I arbitrarily chose B minor because it's my favorite. Songs like Aria of the Soul and Swan Lake are in B minor. Of course, we aren't really going to be actually using B minor, but rather the suspended chords that exist within the B minor scale, like B sus, D sus, E sus, etc. From here, it's really just pressing notes of these chords in a way that sounds nice, which I thought would be really hard, but having this framework to operate on really helped. I installed the free trial of Bitwig, assembled a bunch of notes in a way that sounded pleasant to my ears, then used OBS to record the output to avoid the free trial's inability to export, and imported it into Godot. Quite frankly, I think I went a little overboard with the song, but oh well. Before I show you the song, I also made some sound effects out of clarinet samples for hovering over the grid and 2 different sounds for left and right clicks. Now, without further ado, I present to you my latest creation, God Machine. In the end, I just couldn't help myself, and I resolved the song to B minor. It's my favorite chord. What else can you expect? After finishing the game, I went to submit to Doki Jam, read the rules, and realized that my submission forgot to follow one of the rules, so I didn't submit. Oh well, I guess I probably should have read those first. There are many ways to go from here. When I said this topic is like a cognito hazard, I really mean it. There's just infinite choices, and unlike most computer science projects, Cellular Automata can keep scaling bigger and bigger in complexity. We still only have 2 states and only 4 neighborhoods. The dilemmas lie in the tooling. Unfortunately, I wish I had cooler things to show you, but it's very difficult to find those cool rule sets. It really is mostly randomly enabling and disabling cells and adjusting the ranges in hopes of a cooler output. It's very difficult to comprehend what is actually happening even 1 generation into a multi-neighborhood automaton. Because of this, I would like to do more work on visualizing what's actually happening on any given time step, but you also have to stop and think, is there really any point to this research? Beyond the cool visuals, are there actually signs of life here, or is it just a trick of the mind? If you'd like to play the game yourself and try your hand at creating your own organisms, you can find the Godot project in the description to build yourself, or you can get a convenient build over on my Patreon. Here's the system requirements. As usual, a huge thank you to all my current patrons. Without your support, I wouldn't be able to go see Weapons 5 days in a row. That's all from me. I hope you have a great rest of your day, and I'll see you next time.